When we have some charged particle, it will exert on many other different kinds of particles, positive and negative, some sort of force. This force depends on each pair of particles. However, we can define a metric similar to force that is independent of this other particle. That is, it solely depends on the single particle here. In order to do that, we simply have to take the force between a pair of particles and divide it by the charge of that other particle, often called a test particle. This generates what is known as the electric field generated by our central particle here. Let's consider an example. Let's say we have a positively charged particle of 2 coulombs. At a point, let's say 4 meters away, we can place a small test charge Q0. The electric field at this point is defined as the force divided by Q0. We can calculate the force using Coulomb's law as K Q1 Q0 divided by R squared, because now our 2 particles we can call Q1 and Q0. As this is divided by Q0, we now can simplify the formula to K Q1 divided by R squared. This final formula only depends on Q1 and R, but not on any other charge. Therefore, I know that for this charge here, at a distance of 4 meters all around that particle, the electric field will be equal to this value, kq1 by r squared. In this instance, since the particle is of charge 2 coulombs and of distance 4 meters, we can plug in E equals kq1 by r squared equals 8.988 into 10 to the 9 Newton meters squared per coulomb times the charge 2 coulombs divided by the distance squared 4 meters. Plugging this into a calculator yields 1.124 into 10 to the power 9 newtons per coulomb, because this is squared, my bad. So in a 4 meter radius of this point, at any point along this circle you pick, the electric field will have this value. Some things to note about electric field is that electric field lines will always point away from a positive charge. Hence, this value will be positive. But if I have a negative central charge, then the electric field lines will always point in towards that negative charge. Therefore, in that instance, the electric field will be negative. When a positive charge is placed in an electric field, it will always follow the arrow. You can see in the first example, we have 2 positive charges, which means that they will repel, and this positive charge will follow the arrow. In this instance, the charges will attract, and you can see that the positive charge also follows that arrow. However, when a negative charge is placed in an electric field, it will always travel opposite the direction of the arrow. Here, the 2 charges will attract, so the electron will go against the direction of the arrow. Here, the 2 electrons will repel, so once again, the electron will go against the direction of the arrow. In summary, positive charges will follow electric field lines, and negative charges will follow the opposite direction of electric field lines. Note that because we defined electric field as force divided by some charge, we can rewrite this expression to obtain the force on a charge due to the external electric field. For instance, if I put these 2 particles in an electric field pointed right of magnitude 2 newtons per coulomb, and the charges are 1 coulomb and negative 1 coulombs respectively, we can calculate the force by F equals QE equals, for the first particle, 1 coulomb times 2 newtons per coulomb equals 2 newtons. And for the second particle, negative 1 coulombs times 2 newtons per coulomb equals negative 2 newtons. As we know that positive charged particles will follow electric field lines and negative charged particles will go against them, we know that the positive charge will experience a 2 Newton force to the right, and the negative one will experience a negative 2 Newton force to the left.